Welcome to the Deep Dive, where we plunge into a stack of information and pull out the most important insights to get you well-informed, fast. Today, we're taking a journey into the incredibly versatile world of alkenes and their reactions. These fascinating molecules are like chemical chameleons, so easily transformed into a dazzling array of different compounds. Everything from alkaloids and alcohols to aldehydes, ketones, epoxides, and even cyclopropane rings.
Indeed. And our mission today is really to unpack the fundamental principles, the key reaction types that make alkenes such powerful building blocks in organic chemistry. We'll explore the how behind these reactions, dive into what common pitfalls to watch out for, and crucially, define everything plainly, connecting it to intuitive ideas and, well, its real-world relevance.
Right. Think of this as your shortcut to truly understanding why alkenes are, well, at the heart of so much of the chemical world around us.
Okay, let's unpack this deep dive. We've highlighted how versatile alkenes are. So let's start with a classic addition reaction. What happens when you add a hydrohalic acid, something like HCl or HBr, across an alkene's double bond? And what makes this reaction so, foundational?
Okay, so when you add a hydrohalic acid to an alkene, you effectively convert that double bond into a single bond, creating an alkyl halide. What's fascinating here, and it's a really key insight, is that this is essentially the reverse of an elimination reaction. It shows how these fundamental processes are interconnected. The first crucial step involves the double bond itself, those electrons in the double bond reaching out and grabbing a proton from the acid. This creates a short-lived but incredibly important intermediate.
A carbocation.
A carbocation, right? That's a carbon atom carrying a positive charge.
Exactly. It's missing a pair of electrons, so it's positively charged, and it's usually very reactive. It quickly pairs up with the free halide anion, like chloride or bromide, to form the final alkyl halide product.
Now, okay, so the double bond grabs a proton, but there are two carbons in that double bond. Is there a rule that guides which one actually gets that proton?
Absolutely. And this is where a really important principle called Markovnikov's rule comes into play. It's named after the Russian chemist Vladimir Markovnikov. He observed that when an alkene reacts with something like HBr, the proton preferentially adds to the carbon atom in the double bond that already has more hydrogen atoms attached to it.
So the rich get richer, hydrogen-wise?
Kind of, yeah. And what that means is the carbocation, the positive charge, forms on the other carbon, the one that is most highly substituted with other carbon groups.
Okay, so if one carbon has two hydrogens and the other has, say, two methyl groups, the proton goes to the one with hydrogens, and the positive charge ends up on the carbon with the methyl groups. Why is that specific preference so important? Why does it matter where the carbocation forms?
Well, this preference makes the reaction regioselective. That's a key term. It just means the reaction reliably favors one specific constitutional isomer product over others.
Like it chooses a path.
Exactly. It's like a molecular roadmap. The reaction strongly prefers one route. And this preference comes down to stability. Tertiary carbocations, those are 3 degrees, connected to 3 other carbons, are significantly more stable than secondary ones, 2 degrees.
Okay.
And secondary are, in turn, more stable than primary, or 1 degree, carbocations. Understanding the stability trend is absolutely key to predicting the outcome.
Right, and that begs the question, why?
Yeah.
Why are those more substituted carbocations so much more stable? What's happening at the atomic level that makes a 3-degree carbocation, happier than a 1-degree one?
Yeah. That's a crucial point. Carbocations are inherently unstable, right? Because that positively charged carbon is electron deficient. It's hungry for electrons, carries a full positive charge. Atoms generally try to avoid that. But those alkyl groups, the carbon chains attached, act like tiny supportive neighbors. They subtly share a bit of their electron density, their electron cloud, with the electron-hungry carbocation.
How do they share it?
Through a phenomenon called hyperconjugation. Think of it as a weak overlap. It's between the carbocation's empty electron orbital, its p orbital, and the electron bonds, the sigma bonds, of adjacent CH or CC bonds. The more alkyl groups there are, the more of these weak overlaps you have, the more this positive charge is kind of shared or spread out.
Ah, okay, so it dilutes the positive charge.
Precisely. It stabilizes the carbocation. It's like spreading out a heavy load among several people instead of one person carrying it all. That makes the 3 degrees much more stable than 1 degree.
Makes sense. So it's about sharing the electron load. I've also heard that resonance can play an even bigger role sometimes in stabilizing these positive charges. Is that right?
Oh, absolutely. Resonance is like the ultimate charge-sharing superpower for carbocations. When a carbocation has resonance structures, meaning the positive charge can be delocalized, spread out over multiple atoms through the movement of pi electrons, it becomes significantly more stable.
So the charge isn't stuck on one atom.
Exactly. Imagine the positive charge hopping between several atoms. That dramatically lowers the energy of the whole system. Great examples are benzylic cations, which are right next to a benzene ring, or allylic cations adjacent to another double bond. In these cases, the positive charge is effectively shared across many atoms. That makes them much more stable than even simple tertiary carbocations sometimes.
Wow. So if you were to rank them.
Roughly, from least to most stable would be something like primary, secondary. Then allylic is often similar to secondary or a bit better, tertiary, and then benzylic is usually up there with tertiary or even better. So, roughly. Primary, secondary, allylic, tertiary is benzylic.
Okay, that's a useful hierarchy. Now, you mentioned these carbocations are unstable inherently, and you hinted they can be prone to mischief. What kind of trouble can these intermediates get into? Why do we need to worry about that?
That's an excellent point, yeah. Carbocations can rearrange. They're always looking for a way to become more stable as possible. This means an alkyl group, or even just a hydrogen atom with its electrons, can actually shift, like hop over, from a neighboring carbon to the carbocation center. If that shift results in a more stable carbocation.
Right.
For instance, a less stable secondary carbocation might spontaneously rearrange to form a more stable tertiary one if there's an adjacent carbon that could become tertiary after the shift. You really need to watch out for this, especially when the carbons next to the initial cation center are highly substituted. It can lead to unexpected products if you're not careful.
These shifts aren't just about stability in straight chains, right? I heard they can also involve rings sometimes.
That's right, and it's fascinating. Alkyl shifts can even cause small, strained rings, think 3 or 4-membered rings, to open up and expand into larger, much more stable rings, usually 5 or 6-membered ones.
Why would they do that?
It's all about relieving ring strain. Remember, carbon atoms and stable molecules prefer bond angles around 109.5 degrees, the tetrahedral angle. Small rings force those bonds into much tighter, uncomfortable angles, like 60 degrees in cyclopropane. That's a lot of strain, a lot of stored energy.
So the molecule wants to relax.
Exactly. So the rearrangement happens to relieve that strain, forming a larger, happier ring. So the two main drivers for carbocation rearrangements are achieve a more stable carbocation or relieve ring strain. Understanding this is vital for predicting the actual product.
Okay, so we've seen how alkenes add hydrohalic acids and how those carbocations can rearrange. But what if we wanted to add something really common, like water, to an alkene to make an alcohol? It sounds like there are different ways to do that too, leading to different outcomes.
You're absolutely right. Adding water, which we call hydration, is super important. And we have two main strategies that give us distinctly different results. We can get either the Markovnikov product, where the hydroxyl group, the OH, attaches to the most substituted carbon of the original double bond.
Right, following the carbocation stability trend we talked about?
Or we can get the anti-Markovnikov product, where the OH group attaches to the least substituted carbon, so we can choose.
Okay, how do chemists achieve the Markovnikov alcohol? The one that seems like the normal outcome based on carbocation stability.
For the Markovnikov product, the go-to method is usually oxymercuration-demercuration. It sounds complicated, but the process is neat. You treat the alkane first with mercuric acetate and water. Then you follow up with a reducing agent, sodium borohydride. The clever part is, instead of forming a free rearrangement-prone carbocation, this method uses mercury to form a special 3-membered ring intermediate called a mercurinium ion.
So it controls it somehow.
Exactly. The water molecule then attacks the most substituted carbon of that ring intermediate, and the mercury is later replaced by a hydrogen using the sodium borohydride. Crucially, this avoids those messy carbocation rearrangements, making it a very reliable way to get the Markovnikov alcohol specifically.
Very clever. And what if we want the opposite? The anti-Markovnikov alcohol, where the OH goes on the less substituted carbon. How do we force it to do that?
That's precisely where hydroboration-oxidation comes in. It's a fantastic reaction sequence. Here you start with borane, often complexed with THF, tetrahydrofuran. You react that with the alkene. Then you follow up with hydrogen peroxide and sodium hydroxide. The mechanism for the first step, the hydroboration, is really unique. Both a hydrogen atom from the borane and the boron unit itself add simultaneously across the double bond.
Simultaneously.
Yes, in a concerted step. And they add specifically so the boron attaches to the least substituted carbon and the hydrogen to the most substituted one. And crucially, they add to the same face of the double bond molecule. This is called synaddition.
Synaddition.
Yeah. Later, in the oxidation step, the boron unit is elegantly replaced by a hydroxyl group, giving you the net anti-Markovnikov addition of water.
You mentioned synaddition means they add to the same face. What about anti-addition? And why is this distinction, same face versus opposite faces, so important?
It's absolutely critical for determining the three-dimensional shape, the stereochemistry of the product, especially when you're working with cyclic alkenes, rings. If you have synaddition to a cycloalkene, the two groups you added will end up cis to each other. Think of them both pointing up or both pointing down relative to the ring.
Okay.
In contrast, anti-addition results in trans groups, one pointing up, the other down. They're on opposite sides.
I see. So it dictates the 3D arrangement.
Precisely. And controlling that 3D arrangement is incredibly powerful in fields like drug design or material science, where shape is everything.
Fascinating.
Yeah.
Okay, so we can add one OH group either way. What if we want to add two hydroxyl groups across the double bond? Can we do that?
Yes, definitely. That's a very important transformation called dihydroxylation, making a diol a molecule with two OH groups. It's commonly achieved using a reagent called osmium tetroxide, OO₄, usually in catalytic amounts with something like hydrogen peroxide to regenerate it. The alkene reacts with the osmium tetroxide first, forming a 5-membered cyclic intermediate called an osmate ester.
Another cyclic intermediate.
Yes, these controlled cyclic steps are common. Water then breaks down this ester, regenerating the catalyst and leaving behind the diol. And much like hydroboration, both oxygen atoms from the osmium tetroxide are added to the same face of the double bond. So this is another classic example of a synaddition.
Syn-dihydroxylation. Got it. Very useful for making specific structures, I imagine.
Extremely useful, especially for creating specific chiral centers, which are absolutely essential for many biologically active molecules, like drugs.
Okay, so we've added water, even two hydroxyls. Now let's pivot a bit. Alkenes also react readily with halogens, right? Like bromine or chlorine. And I think I heard there's a neat visual trick associated with one of these.
They absolutely do. They react to form a diallide, meaning two halogen atoms add across the original double bond. And you're right about the visual trick. The reaction with bromine is actually a very simple, common, qualitative test for the presence of alkenes. Bromine water, Br2, dissolved in water or an inert solvent, has this distinct reddish-brown sort of blood color.
Okay.
If you add this colored bromine solution to a sample, and if that sample contains an alkene or alkene, the bromine rapidly reacts, adding across the double bond, and the color disappears. The solution turns clear.
Ah, so if the color vanishes, you know you've got a double or triple bond.
Exactly. It's a quick visual confirmation. Now, the mechanism for this halogen addition is interesting. It's not quite like the HBr addition. The alkene first reacts with the Br2 molecule to form another unique 3-membered cyclic intermediate called a bromonium ion. It has a positively charged bromine in a 3-membered ring.
Another ring.
Yep. Then the free bromide ion, Br, attacks this bromonium ion, but it attacks from the backside.
Backside attack.
Yeah, meaning it attacks the opposite face from where the first bromine bonded. This leads to the two bromine atoms ending up on opposite sides of the molecule in the final dibromide product. So this reaction proceeds with anti-stereochemistry. It's an anti-addition.
Synaddition for hydroboration and dihydroxylation. Anti-addition for bromination. Good distinction.
Okay, that's a great visual test too. Now, we've mostly discussed adding things to alkenes. Can we also break them apart? Cleaving or, chopping up double bonds sounds like a really powerful transformation.
It is indeed, like molecular scissors. A key reaction for this is ozonolysis. It uses ozone, O3, to precisely cleave or cut carbon-carbon double bonds right down the middle.
Ozone, like in the atmosphere.
Exactly, same molecule. In the lab, you generate it and bubble it through your alkene solution, usually followed by a workup step with something like zinc or dimethyl sulfide. The result is that the double bond is completely broken, and you end up with two separate fragments. These fragments end up as either aldehydes or ketones, depending on what groups were originally attached to the carbons of the double bond. Okay, how do you know if you get an aldehyde or a ketone?
It depends on the substitution. If a carbon in the original double bond had two alkyl groups attached, that side becomes a ketone after cleavage. If it had one alkyl group and one hydrogen atom attached, that side becomes an aldehyde. If it had two hydrogens, it actually becomes formaldehyde.
So you can basically just imagine snipping the double bond with scissors and sticking an oxygen atom with a double bond onto each of the cut ends.
Yeah.
Is that a fair visual?
That's an excellent way to visualize it, yeah. You simply snip the double bond, visually speaking, and then cap both resulting ends with double-bonded oxygen atoms to predict the products.
That's handy.
It really is. And this reaction is incredibly useful in organic synthesis, not just for making aldehydes and ketones, but also as a powerful analytical tool. By analyzing the fragments you get from ozonolysis, you can often deduce the structure of the original unknown alkene you started with. It's a very common type of exam problem, actually working backward from products to reactant.
Structure determination. Cool. Is there a maybe stronger way to chop them up, something that might give different types of fragments?
Yes, there is. If you use a stronger oxidizing agent, like hot concentrated potassium permanganate, KMnO4, you also cleave the double bond. This is sometimes just called permanganate oxidation. It performs a similar cleavage to ozonolysis, breaking the double bond. But permanganate is a much stronger oxidizing agent. So the key difference is, any fragments that would have become aldehydes using ozonolysis, meaning they came from a CH bond on the original alkene, get further oxidized by the strong permanganate all the way to carboxylic acids.
Oh, wow. So aldehydes become carboxylic acids.
Correct. Ketone fragments, however, which come from carbons with two alkyl groups attached, are generally stable to these conditions and remain as ketones. So permanganate gives you ketones and/or carboxylic acids, while ozonolysis gives ketones and/or aldehydes.
Different products depending on the reagent strength.
Yeah.
To know. Okay, we've explored adding breaking bonds. Now let's pivot to building entirely new structures, particularly rings. You mentioned cyclopropane rings right at the beginning. How do we make those tricky little three-membered rings from alkenes?
Right, cyclopropanes. One really elegant way is by reacting alkenes with a unique, highly reactive species called a carbene.
Carbene, not carbocation.
No, different species. A carbene is a neutral carbon atom, but it only has two substituents and it possesses a lone pair of electrons. This makes it electron deficient in a different way and very eager to react. For instance, dichlorocarbene, Cl2C, which has two chlorines and a lone pair on the carbon, can be generated pretty easily, like by reacting chloroform, CHCl3, with a strong base. This highly reactive dichlorocarbene then readily adds across the double bond of an alkene in a single step, forming a three-membered cyclopropane ring with the two chlorine atoms still attached.
Neat. Is there another way to get cyclopropanes, maybe simpler ones, like without the chlorines, just the basic three-carbon ring?
Yes, absolutely. For making unsubstituted cyclopropanes, or those with simple alkyl groups, the Simmons-Smith reaction is an excellent and widely used method. This reaction uses a special zinc-based reagent, often written as ICH2ZnI, which is made from diadomethane, CH2I2, and a zinc-copper couple. Now here's the interesting part. While this reagent delivers a CH2 unit to the double bond to form the cyclopropane, it doesn't actually form a free methylene carbene, H2C, as an intermediate.
So it acts like one but isn't one.
Exactly. It behaves as if it were this simple methylene carbene. Because it acts like a carbene in its reactivity but isn't the free species, it's referred to as a carbenoid. It's a highly effective and selective way to make cyclopropane.
Carbenoid. Okay. And what about epoxides, those three-membered rings with an oxygen? I know those show up in things like superglues, so they sound pretty useful synthetically, too.
Oh, definitely. Epoxides are incredibly valuable synthetic intermediates. They are, as you said, a special type of ether, but locked in a strained three-membered ring that includes one oxygen atom.
That strain makes them reactive.
Precisely. That ring strain makes them highly reactive towards nucleophiles, which can open the ring. This makes them fantastic building blocks in organic synthesis. And yes, their reactivity is exploited in things like epoxy resins and glues, where they react to form polymers. Synthesizing them from alkenes is quite straightforward. You react the alkene with a peroxy acid.
Peroxy acid.
Yeah, it's basically a carboxylic acid that has an extra oxygen atom inserted into the OH bond. A common one is MCPBA, metachloroperoxybenzoic acid. That extra oxygen is readily transferred to the alkene's double bond, forming the epoxide ring in a clean, direct reaction.
Very efficient. Okay, finally, we've covered a lot. Adding things, breaking things, building rings. What if we just wanted to simplify an alkene, get rid of that double bond entirely, and turn it back into a simpler, saturated alkene? How would we achieve that?
The simplest transformation, in a way, that's achieved through catalytic hydrogenation. It's conceptually very straightforward. You take your alkene, dissolve it in a suitable solvent, add a metal catalyst, usually something like palladium finely dispersed on charcoal, PDC, or platinum, PT, or nickel, nite.
Like the catalytic converter in a car.
Similar catalysts, yes, noble metals often. Then you expose this mixture to hydrogen gas, H2, often under some pressure. The catalyst helps the two hydrogen atoms from H2 add across the double bond, effectively erasing it and converting the alkene into the corresponding fully saturated alkene.
And does this have a stereochemistry preference, like syn or anti?
Good question. Yes, it does. Catalytic hydrogenation occurs via syn addition. Both hydrogen atoms add to the same face of the original double bond as it sits on the surface of the metal catalyst.
A syn addition again. Okay.
And this reaction is incredibly important industrially. For example, it's used extensively in the food industry to convert unsaturated vegetable oils, which contain double bonds, into saturated or partially saturated fats like margarine.
Wow. Okay, what an incredible deep dive into the reactivity of alkenes. We've gone from adding simple things like hydrohalic acids and water, guided by these really neat principles like Markovnikov's rule and carbocation stability, all the way to chopping up double bonds with ozone, like molecular scissors, and even building complex new rings like cyclopropanes and epoxides. It really shows how understanding these fundamental reactions lets chemists transform simple starting materials into this huge array of useful compounds.
Absolutely. And this understanding of alkene chemistry, it's truly foundational. It's incredibly powerful. It shows you not just what happens in these reactions, but crucially, why they happen. It reveals the underlying logic, the elegance, really, of organic synthesis. By knowing these basic transformations, addition, cleavage, rearrangement, ring formation, and the principles that govern them, like regioselectivity and stereochemistry, well, chemists gain a sort of molecular crystal ball. They can predict outcomes, troubleshoot problems, and even design entirely new pathways to create complex, vital chemicals, everything from life-saving pharmaceuticals to advanced materials.
It really puts it in perspective. So reflecting on this journey through alkene reactivity, what stands out most to you? Maybe consider how these fundamental transformations, these reactions we've discussed, form the very building blocks for countless materials and innovations all around us. From the specific stickiness of certain glues relying on epoxide chemistry, perhaps, to the targeted action of a complex pharmaceutical molecule whose synthesis likely involves many of these steps. These reactions are happening, designed by chemists at a molecular level, precisely dictating the properties of the final product we use every day. So here's a thought for you listening. What everyday object do you think might owe its existence, or at least its key properties, to one of these specific alkene transformations we talked about today? Something to ponder. Thank you so much for joining us on this deep dive. Until next time, keep exploring and stay curious.